What is physical AI and why has it become such a hot topic? Well, most of the AI that you and I interact with in our daily lives today exists digitally. So, I'm thinking about things like talking with a chatbot, that's digital, or using AI for image generation, or maybe using it as a code assistant. These things, they all live in the world of bits and bytes. These are bits. But physical AI, that kind of crosses over into the world of atoms, things in actual physical space. These are AI systems that can perceive their environment, they can reason about it, and they can take action. So let's discuss what physical AI actually is, why it's such a hot topic today, and then also how we can train it. So let's start with the what. So before physical AI was really popular, physical machines like robots, they kind of behaved according to rule-based or scripted instructions, like a robotic arm on an automotive production line. It might wield the same seam in the same spot 1,000 times a day. It's been engineered to be super precise, super repeatable, but it's also super limited. It can only do what it's explicitly programmed to do in an environment that's been carefully engineered for it. But that has changed with robotic AI agents. Those are equipped with language models, so they're models in themselves, and they have something of a general understanding of the world that they live in. And that general knowledge can be paired also with reinforcement learning, meaning trial and error training in simulated environments, to give a robot both broad understanding and specialized skills for a specific task. And I should say that physical AI is more than just robotic arms. It's the smart factories where machines coordinate autonomously. It's energy grids that optimize themselves. It's the fleet of autonomous cars on our roads. Essentially, it's any system that exists in the physical world that can potentially be augmented with AI. So why is physical AI suddenly a hot topic? Why now? Well, there have been a bunch of bottlenecks that previously held back physical AI, and those bottlenecks have to some extent been broken. And the first of those relates specifically to models. And specifically, I'm talking about vision, language, action models, or VLAs. And the name kind of tells you what they do. Vision to perceive the world, language to reason about it, and action to do something. Now, before VLAs, robots could see and act, but they couldn't really reason about novel situations the way that these models can. And we're now seeing open robotics foundation models. And these are trained on massive data sets. Foundation models trained on tens of millions of hours of, say, driving or robotics data. Models that capture general knowledge of real-world physics and object manipulation. And these models are openly available. You could download one of them from Hugging Face. Now, in robotics, there's something called the sim to real gap. That essentially says that robots trained in simulation often fail in the real world. The real world tends to be just a lot more messy than what's modeled in a simulation, but World Foundation models are now generating physics-aware synthetic training data that actually does transform and transfer to our messy reality. And then number three all comes down to compute, and specifically compute efficiency, which has gotten ridiculously good. So processing 20 million hours of video data, that would have taken like 3 years on previous generation CPUs. That sort of thing now takes weeks on current generation GPUs. So these models, they can process a lot more data. So you have better models for simulation, better simulations overall, and faster hardware. That's why physical AI is seeing so much recent progress. All right, let's discuss how to train physical AI, because it's a little bit different to building an LLM where you're training on text and images. This is real world data collection where things move and react to their environment. So that really requires something else. So to train a physical AI model, we will need to start with a simulated environment. So we've got a simulation here. This is like a bit of a virtual world, if you like, where a model can train at scale. So let's say we want to train a robot to assemble parts in a factory. Well, we'll need to create a simulation, and that simulation contains the robot itself, and then it contains all of the parts that the robot is going to work with. It's going to need the actual workbench the robot sits on. We'll need to simulate that as well as well, all sorts of other random things as well, like varying lighting conditions. That's because these random things create different scenarios. So we need to be able to simulate domain randomization, which essentially means deliberately varying everything from different part orientations here to different amounts of friction depending on the humidity in the air. And then once we've done that, we can apply the stage of RL, that's reinforcement learning, which is a whole lot of trial and error. So the robot attempts a task. If it succeeds, it gets a reward, thumbs up. If it fails, it doesn't. Across thousands or maybe even millions of interactions, the robot figures out what works, what doesn't. Now, once the robot hits a certain success threshold in simulation, it's ready for deployment. We're going to go now to the real world. This is reality, where it will work perfectly and we'll move on to simulate something else. Well, probably not. Inevitably, it's actually going to encounter stuff in the real world that wasn't in the simulation. That parts are maybe slightly different, or the surfaces behave in an unexpected way. So we'll need to capture that real world data and we'll feed it back into the simulation, and we'll train again and then we'll deploy again. And this feedback loop between simulation and reality is how these models close that sim to real gap. So that's physical AI, training in simulation so machines can handle our messy real world. It really does seem that we're at the point where the models are good enough, the compute is cheap enough, and the simulation is realistic enough that physical AI is now moving from research labs into real places, factories and warehouses, and even on the roads. AI has always lived in the world of bits, and now with physical AI, it's crossing over into the world of atoms as well.